First one is hybrid system. Second is switch systems. They are similar. Okay. So let's first define what's hybrid system. So the formal definition is hybrid systems are dynamic systems that consist of components with continuous and discrete behavior, which is what I taught on Monday. There are some logic, decision making, and embedded control action, or reactions that are combined in the continuous physical process. The continuous physical process means the continuous dynamics. This logic decision making are discontinuous behaviors or discrete behaviors. So they might be vague, but let's give an example. Here you can see two systems that switch between. So this is the first system indexed by Q0. Second system indexed by Q1. You can say this is 1, this is 2 systems. Maybe you have multiple, you have 3 systems. Basically, the state is Q0, okay, depending on which system you are in, and the state X0. Only one system will be activated given any time. So assume you are in here when t is 0. And in this system, the state is X, which follows this dynamics. So you can see that X have a solution according to this ODE. And that means that the solution of X is always in this invariant set Q0. This is Q1. And the timing to switch between the two is this condition. When G is a function of Q0 and Q1. When under some conditions, maybe this function satisfies some condition, then it will switch from Q0 to Q1 or Q1 to Q0. This condition is G, and there's another G that switch from Q1 to Q0, this system to this system. So G is, we call is the guide or guidance map that when the discrete state transition occurs. Discrete state means Q0 and Q1, and X is a continuous state. And there's a reset map that happens when you switch from here to here. There will be a reset map that could reset the states, because the state, which is X or Q1, can be discontinuous, or we say jump. IMV is the invariant of Q0, for example here. Vague based on this definition. So take a look at the example. So here is the heater, okay, thermal state. In the winter, you might turn on the heat to keep the room warm enough. You turn on the heater in the room, and let go is to regulate the temperature around 75 Fahrenheit Celsius, which is around 20 Celsius degree. So you want to keep the room temperature at 75, but that's quite impossible for maybe a few decades ago. So the control strategy for the heater is, the best you can do is to keep the temperature around 75, which is between 73 and 77. When the temperature is high enough, say 77, then you will turn off the heater. The temperature will go down. Okay, the temperature now is the continuous state. The states cannot jump, right? So state have to be continuous. But you have two discrete states. One is this, one is this. Turn on, you have only two options. Either heater is on or off. So when you turn, and based on different discrete state, you have different dynamics, F1 and F2, right? This is heating up the air and cooling down the air, heating up the air. When the temperature is high enough, you cut off the heater power. Temperature goes down. It reaches to 73. Then at this point, you turn on the heater. So the temperature goes up here and going back and forth. The process repeats. So in this case, what is the discrete state? As I mentioned, this is discrete state 1, Q0 and Q1. The continuous state is X, which is the temperature, and they follow two different dynamics according to the discrete state. So this is an example of hybrid control. That can be modeled by this map, right? Heater is on, heater is off, and based on different discrete state, when heater is on, for example, the X will increase because temperature will increase, otherwise decrease. And there's a condition when you will switch between the two, right? The condition is when the temperature hits 73 or 77. It's the two different guidance map. So eventually, after this controller for the hybrid system, you can see that the temperature can be controlled between 73 and 77, which is around 75. Here's the map, and you have two guide conditions. If it's below, temperature is below 73, okay, then you will turn on. Heater will from off mode to on mode, and the two highs, you will cut the power. So it's continuous state for the temperature, and this is discrete state, which includes on and off. Second example is the bouncing ball. So this is time axis, this is the height axis. So for example, you drop a ball from the height of y. X is the position of the ball. It is the height of the ball, right? And initially it's what it was. Y is the position of the ball. So the Governing equation or the dynamics of the ball is y double dot equal to minus g. So y double dot is the acceleration. The only force in the system is gravity. Okay. The dynamics, the state is continuous all the way until it hit the ground. And what happened after it hit the ground? Some discontinuous behavior, we say it's collision, right? Y plus means time before you hit the ground. Y plus means that the position after you hit the ground. Y minus is the position before you hit the ground. Okay, but they are zero because plus and minus is just a small difference. After it hit the ground, the velocity will change. Y dot is velocity, and plus means after you hit from the ground, the velocity will change the direction, which is minus. C is the discount factor. Before it hit the ground, the velocity might be 100. After it hit the ground, it might become 10% off, which is from 100 to 90, right? So discount factor is 0.9, right? So this is the change of velocity after the impact from the ground. This can be described by your hybrid system, which is this. But in here, there's only one dynamics, which is the acceleration is under effect by the gravity, right? And this transition, it transits from the same state to the same state, right? And it happens when you hit the ground, which is x1 equal to 0, and velocity, x2 is the velocity, is minus. After you hit the ground, this velocity will change the direction, which become positive here, okay? So this behavior can be modeled by hybrid systems, okay? And before, if you use conventional dynamics, you cannot model this behavior because obviously there's a discontinuous state in terms of velocity in the system. Before, what we cover in this class, this semester, before this course, is continuous dynamics. This is the first time you see the discontinuous dynamics. And here's the case of the pendulum fixed that connected to a car, and you want to swing up the pendulum to the upper right position, okay? And you can use switch control. And here you will see three different procedures. Here you pump up the energy, which happens when in this position where the pendulum is on the downside. Okay, you want to pump up the energy so that the pendulum can swing up to the desired position, which is right up. So you pump up the energy for the first step. Second, you wait the pendulum to be, might oscillate around here, so you wait. When it's close to the right position, you remove energy, so you can stabilize the pendulum to the desired position. This can describe the procedures. And here's the controller you design for each phase, right? In this phase, you design this controller that can use to pump the energy to the system. And here, the controller doing nothing, right? It's zero. It does nothing. And here, you remove energies. So compare here to here. One is minus, one is positive. So the different functionalities. Second, switch systems. It's very similar to the hybrid systems. For example, you have continuous state X. You have discrete behavior, which is you switch the system from one system to another system. For example, from F1 to F2. F is the differential equations. but the x, the state here is continuous. The only discrete state is this sigma, which determines which system, which dynamics you are in, okay? So only one of these subsystems will be activated at one time. There are some rules. Here is state dependence region. So the decision making of this sigma x can be determined by function of states, why we call state dependence region. If you have four systems F1 to F4, and you define some state dependence regions, which is these blue lines, that means that when they state, this is phase portrait, right? So every point on this surface is a state. When your state is here on the boundary of this line, they will switch to another system. Okay, that's state switching dependence. State dependent switching. So the objective is you design the switching condition. You design this surface, okay, these blue lines, such that this trajectory, this red line, which is the trajectory of solution, right, which is the trajectory of x, can be stabilized to the system, to the origin, to our desired position. So you need to design these blue lines, the switching conditions, and maybe the controller for each subsistence. So you have two things to do, right? Design controllers and switching conditions. So secondly, commandable functions. We have mentioned that you have many subsystems to switch between, right? But how can you show, what's the tool that can be shown to demonstrate the stability of the system? One of the tools, not the only tool, is commandable functions. To define commandable function, first we need to consider switch systems, okay? So if you consider this x star equal to ax, that's what we taught before, right? And this is a linear system. And A determines the dynamics, natural dynamics of the system. But now you have different A1, A2, because Qt is belong to a set from 1 to n, okay? You have different subsystems to switch, okay? And the objective is you want to control the state, which is continuous, okay? Even though it's switch between systems, the state is still continuous, right? There's no jump on the state. For example, the temperature cannot jump, right? It's a value that never jumps, even though it's switched between systems. And the objective is control the state to 0. For asymptotic stability, you need to construct a Lyapunov function here, okay? V and V dot is negative definite as long, okay, negative definite. And what is common Lyapunov function? For example, there's a quadratic function, which is this, okay? It's a PD function. And this P is unique, and that satisfies this inequality. The P is unique, is only the same P, but for different subsystems. For example, if you have 3 subsystems, you have 3 A1, A2, A3, right? So you have A1, A2, A3, 3 different inequalities to be satisfied. If you can find that P, then V is a common Lyapunov function. Then we can say the state will be stable no matter how you switch between systems. Maybe back to here, you have F1, which is A1x. Okay. So this is a system. Assume that we don't consider controller here. We just consider systems, 3 different systems. And only one system can be activated at a time. Is the system stable or not? The overall system. How do you prove that it's stable or not? So the tool is common Lyapunov function. So the condition is, given a Lyapunov function, okay, the P is unknown, you need to find P. And the way to find P is you need to satisfy these 3 conditions. If you can find the P that satisfies these 3 inequalities, you can say this Lyapunov function is common Lyapunov function. Okay. Okay. And the system is stable no matter how you switch. Okay. It doesn't matter the switching sequence. Okay, you can arbitrarily switch between systems. Okay, so how can we prove this? So V is this, and V dot is P X dot plus, okay, and you substitute the X dot here. X dot is equal to AX. For example, A1X. So if this part is negative definite, so which is the condition of the first condition, right? If this condition is satisfied, then the first V dot will be negative definite, at least for the first subsystem. And you can expect that if you substitute the stability, the dynamics of second system A2X into layer, the V dot will still be negative definite, right? Same as the third subsystem. That means that initially, if your V0 is here, okay, V0 is here, and at this time, from T0 to T1, from T1 to T0 to T1, assume that activated system is system 1. Okay, this is switching signal, right? Anytime only one system is activated, and let's say this time the first system is activated, A1X is activated, right? What happened to the ripple function here? According to the V dot, right? V dot, and you substitute A1X, and you can see that V dot will be negative definite. That means that V will decrease. V will decrease, right? And because X is continuous, so V is also continuous. In the second time slot from here, V will continuous. And if the second system is activated, and again V dot is still negative definite, so it will continue to decrease, but the decreasing rate might be different because this value could be different. Okay, but no matter how you switch between the systems, no matter here's 1 or here's 2 or 3 system is the third system is activated, it always decrease, right? Same as here, same as here. So eventually, you know, V will goes to 0. Okay. So that's why this is the condition to find P, and P defines the Lyapunov function, and we call it common Lyapunov function because there's only one Lyapunov function more for multiple systems. Okay. So I remember that some of you asked me how to find Lyapunov functions, like 2 weeks ago when we taught Lyapunov function, right? Because at that time, given a Lyapunov function, I always just give you a Lyapunov function, and I did not say how to design a Lyapunov function, right? But this is one way to design Lyapunov function. Okay, you can set up this inequality in the MATLAB, and that result will return you the P matrix. So another condition you need to set is P is greater than 0. P is PD in your MATLAB. Then you guarantee that this P is positive definite and it's a common Lyapunov function. And if you can decide which system to switch, you have multiple systems. You can choose which system to switch. If you have that freedom, then you can choose the best one, which is according to least law. Okay, so this X transpose F is you can consider as kind of V dot, the decreasing rate and you choose the minimal one. The existence of common developable function is only a sufficient condition, but not necessary one. Which means that if you can find a common developable function, that will be great. It guarantees the system will be stable. But if you cannot find one, that doesn't mean system is unstable. Okay, there's still some gap you need to figure out because sometimes it's too conservative and even infeasible to find a common developable function. And it doesn't imply the system is unstable. Like this is stable. But if you can find a common developable function, common developable function is in the set of stable. If you can find one, that guarantees stability. But if you cannot find one, that means it can be here. Okay, it can be somewhere here. That was not the case for a common developable function to exist, but it could be still stable. The fourth topic is interesting because when you switch between unstable systems, what happens? The question is, can you stabilize the system if these systems are unstable? Can you design a switching law that guarantees stability of the overall system, even though each subsystem is unstable? And the answer is yes. For example, if you have two unstable subsystems, A1 x star equal to A1x and A2x, A1, A2, all the eigenvalues are positive. That means both systems are unstable. Can the overall system still be stable by appropriately design a switching condition? Can you? Is yes. For example, here you have two subsystems, both are unstable, and by appropriately switch, this is A1x, this is A2x, and by appropriate switch, so in here, if you start from here in A1x, the solution will go this way. If you are here, the solution will go this way. And this is the dynamics or the trajectory when you stay at A2x. If you properly design this switching condition, which is this line. Initially, if you are at system 1 and that will, the system will push the solution to here, right? When you hit the switching condition, it switches to the second system, A2, and the solution trajectory becomes to here. And that hits another switching condition and it switches from 2 to 1. And switch. Eventually, that guarantees that solution will converge to the origin. Okay. So that's the example when you switch between unstable systems. So that's the phenomenon that it's hard for you to imagine before this class. Again, the way to find that condition, first you can try common developable functions, if it exists or not. There's another tool called multiple developable function, Lyapunov-Like functions. Multiple means it's more than one developable functions. It can be multiple developable function. Multiple developable function be used to analyze an overall system. There are families of piecewise continuous and piecewise differentiable functions that are concatenated together to produce a single non-traditional developable function, multiple developable function. You merge those to single developable function. So the way we say non-conditional is because the property, the way we define developable function is a bit different. So a family of developable function like function, Lyapunov-like function is this. You have index I, and I is between 1 to Q, is the set of 1 to Q, such that each vector field, which means each subsistence, have its own developable functions. So if you have Q number of subsystems, then you will have Q number of developable functions, the corresponding developable functions. So the condition theory to use to prove stability is this. So in this example, we have two developable functions, V1 and V2. This is time axis. This is the developable function axis. So in this time slot, the first system is activate, Q is equal to 1. Later is 2, 1, 2, and 3. So in this time slot, you can find the corresponding developable function, which is V1. And V1, it has to decrease. And the way to make it decrease is you can design the controller for the first system. Same as the way we taught before, right? You design controller for a single system. that can be achieved. So the Lyapunov function will decrease. When the switch happens, the switch between Q1 to Q2. In this time slot, the corresponding Lyapunov function is V2, and it has to decrease as well. But what happens in the same time slot to V1? It might increase, but it's fine. If it increases, that's fine. The most importantly is when you switch back to Q1, from Q2 to Q1, which is this time point, this value, V1 value at T2 has to be smaller than V1 at T0. Okay, you compare these two. So here's Q1, right? So when we switch back to Q1, okay, we compare these two time points. This value had to be smaller than this one. We compare the same Lyapunov function, V1. In the second system, when you switch back to Q2 here, you need to make sure this value is smaller than this value. And if that happens, that means that eventually V1 will decrease to 0. V2 will also decrease to 0. So the reason to introduce multiple Lyapunov function is, given the two systems, there doesn't exist a common Lyapunov function. Then you have second options. But again, it's very conservative. The way to switch this is very conservative. So again, it's a sufficient condition for stability. To conclude what I just said, the condition for stability is this. Given a family of Lyapunov function, VQ, that corresponding to each vector field AQX for each subsistence. So Q is the subindex. And for any I smaller than J, and let Ti smaller than Tj. And Ti and Tj index the same subsistence because Qti equal to Qtj. Remember, this is the index for the discrete systems. Qti, Qtj means Qti, Qtj. They are belong to Q1, but at different time slots. Same system, different time slot. Same system, equal sign here, but different time slot, T1, Ti, Tj. For the same systems, right? Qt at different time slot, Qti, Qtj. The same Lyapunov function has to decrease because this time Tj is greater than Ti, same as Tj plus 1, Ti plus 1. So you compare the same Lyapunov functions at different time, but the tendency is it has to decrease because here is a minus. So example, again the same system, okay? The system we just mentioned, 1 and A2. You use system 1, use system 2, system 1, system 2. So the way to design this switching condition, these two lines, is that you find P1 according to A1. It satisfies this condition. A1 transpose P plus PA1 will be a negative definite matrix. So that V1 in this system can decrease. And V2 in this system can decrease. Here we use V1 and V2, V1, V2, V1, V2. So the first time when you stay at system 1, the Lyapunov function decrease. But during the second time when the second system is on, the Lyapunov function increase because it goes from here to here, V1, and this is V1, right? And at this time, this V1 increase from here. But that's fine. What we really care is the V here had to be smaller. This V had to be smaller than this V1. V1 has to smaller than the previous V1, smaller than the previous V1, and it's fine. So eventually, the system V1, V2 will both go to 0. And this is the corresponding Lyapunov function, which is X transpose P1X, X transpose P2X. And for each Lyapunov function, okay, for each subsystem, the corresponding Lyapunov function has to be positive definite, Vita has to decrease.